These are notes over stoichiometry, and so basically what stoichiometry is, it's predicting the future. So we are going to be able to tell how much we're going to make, how much we're going to use, what's going to happen during this reaction before the reaction even starts. Okay, looking at the reaction, and this is a little bit of a review. So if we start with a balanced reaction, this tells us that we have reactants on this side, and these reactants are the ones that are going to mix together and form the product. And then we also have the product, which is here on the right side, and this is what we make. Then we have these coefficients to tell us, and of course there's an assumed 1 coefficient there, that tell us how many moles of each, or how many particles of each we use. So in our example, 2 Mg plus O2 gives us 2 MgO. Our reactants are Mg and O2. Our product is MgO. We use 2 Mgs and 1 O to make 2 MgOs. So our ratio is 2 to 1 on the Mg to O2, and then it's 2 to 2 for the Mg to MgO, and it's 1 to 2 for the O2 to MgO. So what does this mean? Well, we can use this ratio to predict how much reactants we need or how much products we're going to make. So for example, if I had 4 moles of magnesium, I can make 4 moles of magnesium oxide, because I know that for every 2 moles of magnesium, or for every 2 particles of magnesium, I'm going to make 2 particles of magnesium oxide. For every 2 moles of the magnesium that I use, I only need 1 mole of the O2. So I only need about half the amount of O2 than magnesium. So in our example, if I have 4 moles of magnesium, I only need 2 moles of O2 because I only need half. Okay, when we're looking at this, there's 3 stages, there's 3 parts of the reaction. We have what we have before, so you're starting out, this is what you're given in lab, this is your supplies. Then we have the change, and this is how much of the substance is used. Sometimes we don't use up all of a chemical that is a reactant, so we'll have some left over. The change tells us how much of that we are actually going to use. Then we have the after, and this is more of like the product side, and this is what is left over if we don't use all of our reactants. This is also how much product is created. So let's get through and start doing a practice. Here's an example. Hydrogen sulfide gas, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. How many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide? Okay, first step, write the equation. So we're going to zoom in a little bit here. Okay, we are looking at the hydrogen sulfide. So hydrogen is a +1, sulfur is a -2, so this is going to be H2S. Burns in air, so usually if we're burning stuff in air, we're going to be dealing with O2. And it makes sulfur dioxide. Well, that means we have an S and an O2 because we have di, and we have water. All right, so putting those all out, we have H2S plus O2 gives us SO2 plus H2O. And we need to balance this equation. We have, let's see, we have 2H, isn't it balanced? No, we need to do a 2 here to balance out our O's. So that means I have 4 H's on this side, so I need 4 H's on this side. That kind of doubles our sulfur on the reactant side, so we need to put a 2 here for sulfur on the product side. Adding up all of our oxygens, we have 2 times 2 is 4, plus this 2 times 1 is 2, so 4 plus 2 is 6. So we need to make this one 6. So now we have our balanced equation. All right, now that we have our balanced equation, we can start filling in the before row. So our problem says that we're looking for how many moles of oxygen gas would be needed to burn 2.4 moles of hydrogen sulfide. So we need to put our 2.4 moles of hydrogen sulfide into our equation, or into our table. So that's a before. We have 2.4 moles. And it says that we are burning with oxygen gas. Well, there's lots of oxygen gas in the air, so this, instead of putting a number, we just write excess, because we've got a lot of extra. Okay? We haven't reacted anything yet, so we're going to put a 0 moles for the SO2 and 0 moles for the water. Okay, now we need to determine the change that we have. We're going to use up all of the H2S. And we need to figure out how much of the O2 we're going to use. So we have a 2 to 3 ratio of the H2S and the O2. So we can set up a proportion. 2 of the H2 to 3 of the O2 gives us 2.4 up here, and if we solve for x, it ends up being 3.6. So we're going to take away 3.6. So that's why I'm using these negative signs in front of my change, because we are removing the 2.4 H2S and the 3.6 moles of O2. We are taking them away and breaking them down to make our products. Now, we have a 2 to 2 ratio for our products, so the amount of moles used here is going to be the amount of moles that we gain here. So we're just going to put in 2.4, and these are positive numbers because we are making them, we are adding them, so sometimes we put a little plus symbol in there. Okay, so now we do some math, and we fill in the after row. So we have, in our H2S, we have 2.4, and we use 2.4, so we're left with 0 moles here. For our O2, we have a ton, we use 3.6, so we still have some left over, so we call that excess. Then in the SO2, we had 0, but we made 2.4, so we're to 2.4 moles. And then the same with the water. So these, basically, you can look at it as a big 4 separate addition or subtraction problems. Okay, next you answer the question. So our question asks for how many moles of oxygen gas would be needed. And we know that we used 3.6. So it's going to take 3.6 moles of O2 to react all of the 2.4 moles of H2S.